Hello. Hello, everyone. You should be able to hear me. Oh, it's just one person for now. Hello. Okay. Right. So people are coming in. Excellent. So let's start. Let's start. And I've prepared two things for you today. So basically, a little bit of 3D geometry and a little bit of EM induction. On the 4th of January, so there's no webinar next week, but on the 4th of January, we're going to have a guest speaker about EM induction. Okay, so I'm going to share my screen and let's get going. 3D geometry and EM induction. So first we're going to go through some 3D geometry and then to EM induction, to the exciting part. All right. So let's get going. The base of a right prism. So a right prism is where the base is perpendicular to the sides. So basically like this. Not a pencil. A pencil, an example of a right prism. And here, draw lines. So this is a right prism. Okay, find the diagonals of the prism. So let's see what we have. We have the base is A. Base is A, and the height is 3A. Okay, so find the diagonals. So there are several diagonals. So one diagonal goes like this. That's one diagonal. The second diagonal goes like this. Now, are there any other diagonals? Well, different, I mean, different length. So this diagonal, this diagonal. This diagonal is going to be the same. So yeah, that's the only two diagonals that go through the prism. Of course, there are diagonals of each side, but that's not 3D anymore. That's hexagons and rectangles. So find the rectangles. So what do we do here? Well, we try to find a triangle. We always try to find a triangle that it gives us some information, and then we use very benign trigonometry or Pythagoras. So let's have a look. So we want to find this side. Let's do it in green. So this side, we know that this side is equal to 3A. We need to find this side. And well, to find this side, there's different things we can use. Well, this is A as well. And let's label it. So A, B, C. So AB we can find using the cosine rule. Cosine rule. AB squared is A squared plus A squared minus 2A squared. Cosine 120 because we know it's 120 degrees. Okay, so that's 2A squared minus 2A squared multiplied by cosine 120, which is minus a half, which gives us 2A squared minus plus A squared, which is 3A squared. So AB is equal to cube root of 3A. That's pretty neat. So the square root of 3A and 3A. And then we use Pythagoras because this AB is in the plane of the base. Therefore, AB is BC is perpendicular to AB. So it's a right angle triangle. Therefore, we have AC squared is AB squared plus BC squared. So AC squared is AB squared, which is 3A squared plus 9A squared, which is 12A squared. So AC is square root of 12A, which is 2 square root 3A. So that's one of the diagonals. So 2 square root of 3, 2 square root of 3A. Perfect. So it turns out that this side, AC, is double AB. What does that tell you? Well, that tells you that this angle is 30 degrees. 30 degrees, because if you have if the hypotenuse is twice the length of the opposite side, the angle is 30 degrees. All right, now we're looking at the other one, and the logic is exactly the same. So you label it ADE, and you try to find this triangle here. And in a similar way, you have AD. Well, AD is actually equal to 2A, because if you think about it, how a hexagon works, if you know anything about a hexagon, you will agree with me. A hexagon is made up of 6 equilateral triangles. And if this side is A, and this is A, that means this is A and this is A. So AD is 2A. And DE is 3A. DE is 3A. And that means that AE is very simple. So AE is square root of 9A squared plus 4A squared, which is square root 13A. So look, the basic thing that you need to understand is that that all you need to do is find a triangle and apply trig and apply the Pythagoras theorem. That's pretty much like 90% of the cases. You just the hard part about 3D geometry is trying to imagine stuff. But if you always focus on looking for a triangle, looking for a suitable triangle, you should be successful in all your endeavors, in all your 3D geometry endeavors. Right, moving on. Find the volume of the prism. Well, it's I mean, I just put it in case. The volume of a prism is obviously the area of the base times the height. So to find the area of the base, you could, well, you find the area of a right angle triangle. Side A, A. What is the area? Area. I could think of 17, probably 17 different ways of finding the area. I'm going to use a weird method to find the area of the triangle. I'm going to use Heron's formula, and the formula goes like this: square root of p multiplied by p minus a multiplied by p minus b multiplied by p minus c. Has it if you've seen this formula, type 1 please. If you don't know what this formula is, type 0. All right, half and half. That's good. So p is half perimeter. If you have a triangle and p is the half perimeter of the triangle, a, b, c are the sides of the triangle. So perimeter is a plus b plus c, but it's half perimeter, divide by 2. So half perimeter in this case is a plus a plus a, divided by 2, which is 3 over 2a. And then we do area is equal to the square root of p, which is 3 over 2a, multiplied by p minus a, which is 3 over 2a minus a, which is 1/2 a. And this is a half a. And this is a half a. And this is going to be half a multiplied by half a multiplied by square root of 3, which is square root of 3a squared over 4. And that's the area of a right angle triangle. P's half perimeter. Half perimeter. Perimeter. Okay. And yeah, so that's the area of right angle. Oh, sorry, not right angle triangle. A equilateral triangle. That's the area of an equilateral triangle. And there are 6 of those. So the volume is area multiplied by height. And the area is made up of 6 equilateral triangles. So 6 multiplied by square root 3a squared over 4 multiplied by height, which is 3a. And that will make it, we can simplify that, 3, 2, 9 square root 3 over 2 a cubed. And that's the volume of the prism. So that's B. And C, what do we need to find in C? Angle between the longest diagonal and the base. Well, as I said, angle between the longest diagonal is AE, because you can't make a longer diagonal. Longest diagonal is AE. So let's write this down. Longest diagonal is AE. Angle between a line and a plane is equal to the angle between the line and its projection. Okay, that's important. We need a definition of the angle between a plane. So if you have a plane and a line, so this is a line passing through a plane, line L, passing through plane, let's say alpha. Okay. The angle between L and alpha. Alpha is the plane, L is the line. We need to find the projection. So projection of the line. So it's like the shadow. Projection of a line onto a plane is like the shadow of this line. So if you imagine light falling onto the line from the top, and it makes a shadow, and that shadow is called the projection. So let's call it L alpha. So L alpha is the projection of L onto alpha. Now the angle between a line and the plane is defined as the angle between the line and the projection. So this is theta. Does that make sense on a scale of 0 to 10, please? Do you understand what when we say the angle between a line and a plane? Does everyone understand what a projection is? Okay, good. Love it. Excellent. Now we move on and say, okay, so the line AE, we need the angle between AE and the plane ABD. ABD is a plane, AE is a line, and AD is the projection of, so I'm going to copy that and place it here. Yeah. So AE is a line, ABD is a plane, angle between, sorry, the plane, AD is the projection of AE onto ABD. Now, and that means the angle between AE and the plane is this. This is the angle that we're looking for. So angle theta is equal tan, the inverse tan of ED over AD. And that should be quite simple. So ED is 3A and AD we've established that's 2A. So it's A cancels, tan of 3 over 2. Well, look, when you do maths properly, you would say that it's just arctan 1.5. That's the answer, okay? But you can calculate it at the exact value, 1.5, which is 56.3 degrees. 56.3 degrees. Well, different projection give the same angle. You can't have different projections. There's only one projection. Well, I mean, there's one orthogonal projection. That means at a right angle. Does that make, like, if you have a plane, um, if you have a plane and you have a line, there's only one projection that goes, well, it's like the shadow. You can see shadow, but the light has to come from exactly vertical. Yeah, the light is falling. That there's can only be one. Right. Okay. So you might you've done some of this last week. You've done some of these things. I'm just gonna recap. Construct the cross section passing through M, R, and P. M, R, and P are points on a cube, and you need to construct the cross section. So what do? Well, you draw a line. So you need to find the plane MRP. So we need to find how this line goes further. Does it go like this? Or does it go like this? Like, where does the plane cut the cube? Okay, so you need to find the shape of the cross section. Well, to do this, we need to find where MP meets this line. Let's call it AB. So we draw the line AB. And we extend MP until it meets the line. So this point is also in the plane. So point, let's call it MPR N. N belongs to the plane. Okay. Now we extend A. We extend a whatever that is. We extend this line, and we extend this line, and we get a point. Let's call it T. So T belongs to the plane. So now we can construct Tn. And that's Tn is, so Tn, A, B, C, D. Tn belongs to the plane A, B, C, D. So N and T both lie in the plane A, B, C, D. And therefore, we can construct we can draw the line BC, extend the line BC, and this is where the plane meets. So let's call it Q. Q belongs to the plane. And now we can draw the line PQ. And this is where the plane meets. This is where the plane meets this side. And then you can just take a nice color and draw the cross section. Okay. So this is the cross section passing through. Well, you could do it in a different way. You could draw a line P. You could draw a line parallel to MR. That's another way of doing it. All right, let's see what we have here. We don't have too much time left. I will stop 3D geometry at quarter to 7, just to make time for electromagnetic induction. So here we need to find the shape of the cross section. So we draw. So first we draw what we have. We draw RP and we have RM. Now we extend. What do we extend? Well, we need to find the line along which it crosses P, this plane. And does it have to be parallel? Okay, so if a plane cuts two parallel, so you can see that this plane, the back side, let's label it properly. A, B, C, D, E, F, G, H. So plane A, no, sorry, B, C, G, F is parallel to A, D, H, E. The plane BCGF is parallel to the plane ADHE. Therefore, if a plane cuts both parallel planes, the lines of intersection are parallel. This kind of makes sense if you think about it. If you have two parallel planes, and a third one that cuts both planes, the lines along which they cut are parallel. They have to be. And that means that we're looking for point X. We're looking for a point that is parallel to. We're looking for a line that is parallel to RM. So we take RM and we copy it, and we just draw a parallel line. Well, there are different various ways of how you can do this, and this way you can find the point. All right, so that's the first thing to do. Bam. And then you draw a line parallel to PR. So you take PR. And move it here. This is where this line meets, and now we have the projection. Now we have the whole projection. Bam. Bam. Here it is, and that's the cross section. So not the projection, the cross section. Okay, the next one we have, well, very similar one. We have this line passing through, and okay, we don't have much else. Well, we can extend this line down. We can extend this line. So now this point A belongs to both planes, the side plane and the bottom plane. So we can draw the line AM. And line AM crosses this line. It has to be because it's in the same plane. So that's one. So we've got bam. And now we need to find where we can extend this line. And we can extend AM. And this is where this AM meets the back plane here. And that means you go through here. And now you can construct the cross-sectional plane. Here it is. And this is the shape. Quite an interesting cross-section. Okay, and this one, now P is here, M is here, so we can draw a line like this. Can't draw much else, so what can we do? Well, we can extend this line and see where it meets the base plane. So this is the point where line PM meets the bottom plane. All right, so we draw the line R. Okay, so now we got the first point of the cross section. Okay, so we found this side on this side. What happens next? Well, we carry on, we extend this line that way. We draw this line, and this is the point where this line meets the well, this line meets this line. Okay, so this point is in that plane. And this point is also in the back plane. Therefore, you can draw a line like this, and this is fully lying in the backwards plane. And therefore, you can draw a dot. There's a second dot, 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 and choose a different color. And here's your cross section. Okay, same shape of the cross section. All right. So cross sections are fascinating, and this really gets you going into the ideas of planes and lines and where lines and planes meet. So if you what my advice would be to take a screenshot of every single one of them. So here we go. And just practice. Practice doing the same thing. Practice doing the same thing, and here. Okay. Practice doing the same thing and make sure you get the same result as me. Okay. So please give it a go. This is a very important exercise for your 3D thing. Okay, moving on. Theorem of three perpendiculars. It's kind of obvious, it's kind of straightforward, but let's talk about it. If a line is if a projection of a line is perpendicular, sorry, if a line is perpendicular to a line in a plane, then the projection is also if line L is perpendicular to a line let's call it M, in a plane, then the projection of L is also perpendicular to M. Oh, what on earth does that mean? Well, look, if you have a plane, then you have a line in that plane. So there's a line in that plane. So line M, and this is the plane alpha. So M belongs to alpha. Now, there's another line, line L. Line L. And L is perpendicular to M. L is perpendicular to M. Now, L has a projection. And let's say L star is a projection of L. L star is a projection of L. That means, according to the theorem of three perpendiculars, L star is also perpendicular to M as well. Okay. And it works the other way around. If the projection is perpendicular to a given line, then the line itself is also perpendicular. Okay, so we have, if L is perpendicular to M, then L star is perpendicular to M. Also, if L star is perpendicular to M, then L is perpendicular to M. This is the theorem of three perpendiculars and its inverse. Okay, so let's have a look. ABCD is a rhombus. Show that MO is perpendicular to BD. MO is perpendicular to BD. And of course, in all examples, A is perpendicular to ABCD. So if A is perpendicular to, that means MC is perpendicular. MC is perpendicular to ABCD. That means OC is the projection of OM. Okay, so OC is the projection of OM. That means, and because it's a rhombus, that means OC is perpendicular to BD, because the diagonals of a rhombus, diagonals of a rhombus are perpendicular. So OC is perpendicular to BD, and that means if OC is perpendicular to BD, therefore OM is perpendicular to BD, according to the three perpendiculars theorem, the theorem of three perpendiculars. This is how you do a problem on, well, show that problem, a proof problem. All right. Next one. Show that AB is equal to AC. AB is equal to AC. Basically show that this is a equilateral, no, isosceles triangle. Okay, so it is given that MD, so AD, if we draw AD, AD is a projection of MD. Projection of MD. And that means that because MD is perpendicular to BC, that means that AD is also perpendicular to BC. This is according to the theorem of three perpendiculars. All right, so AD is perpendicular to BC, and we have D is the midpoint, and therefore BD is equal to CD. Now, AD is equal to AD. Because the common side. And what else? And it has angle ADB is equal to the angle ADC. The angles are the same. So we have this angle is equal to this angle. We have this side is equal to itself. And this side is equal to this side. And therefore, triangle ADC is congruent to triangle ADB, because it is side angle side congruency, and therefore AC is equal to AB. I don't know if it was easy to follow. I don't know. Okay, I'm running out of time, and I really want to switch to physics. How well did you understand the last question on the scale of 0 to 10, please? There's no shame of saying 7. So please, if it's a 7, do say 7. But these are 10s. Good. Okay. Moving on. So physics, EMF, and emotional EMF, and electromagnetic induction. It's an emotional topic for me because I love it so much. Students tend to find it the hardest topic in all physics. I think for the same reason why 3D geometry is hard. Because in magnetism, you always have to think in 3D. You have to disregard your two-dimensional world, which you are used to. Yeah, your forces always usually in 2 dimensions, projectile motion, 2 dimensions, all physics in 2 dimensions, except when you get to magnetism. And magnetism simply doesn't work in 2D. All right. And okay. Have you heard of motional EMF before you read the assignment? I assume you've read it. Yes or no? Okay. So you've heard about the motor effect, right? The motor effect says if you have a current move in a magnetic field, there's a force on that current. Right? The motor effect, so if you have a current in a magnetic field. But an electron moving through a magnetic field has is current because it's a moving charge. A moving charge by definition is current. So if you have an electron moving through a magnetic field, that's current. Okay, so let's have a look. We have a metal rod moving through a magnetic field at some kind of speed, let's say velocity v, and the length of that rod is L. The magnetic field is B. B is the magnetic field. Of course, it's a vector. Velocity is also a vector. You have, and if it's a metal rod, inside it has electrons. It has free electrons inside. So let's look at a single electron. And because it's an electron and it is moving, that means there's a force acting on the electron. And we can find the direction of that force by using the left-hand rule. So the first finger is the field, so field goes into the page. The second finger is current, but it's a negative particle moving to the right. That means the current is to the left. So current is left. Current is left. Field is into the page. Therefore, the force is going to be down. Force, field, and current. I'm talking about motor effect. The motor effect on a particle, on an electron. So the electron will experience a downwards force. It's a magnetic force, and we know from we know the Lorentz force. The Lorentz force on an electron is B Q V. Of course, the charge of an electron is E, so you can say it's B E V. Okay, that's the magnetic force. But if as the electron, because the electrons are being pushed down, that means that there will be the electrons will gather on the bottom of the rod. Okay, the free electrons are pushed down by the magnetic field. The magnetic field. Does everything make sense so far? On a scale of 0 to 10, please. Please type in the chat. 0 to 10. Okay, it is AB, Andre. Very good. Okay, so we have electrons which are moving through a field. That means that is current, and so they are moving. So they will be pushed down. This is like the whole. No, that's well. It is like the Hall effect. It's like a slightly different version of the Hall effect. Pushed down by the magnetic field. So the electrons will gather on the bottom end of the rod. So the bottom will become negatively charged because the electrons are being pushed down. And that means that the top will become positively charged. And if you connect a voltmeter to the top and bottom, it will register a voltage. So by just moving a metal rod through a magnetic field, you will have a voltage at the end of the rods, at the ends of the rod. Now, this imbalance of charge produces an electric field. And the electron that we are looking at will be pushed away by the electric field, because now there's an electric field from the bottom. There's an electric force because it's being pushed away from these electrons. These electrons repel this particular electron. And now we have a balance. We have a balance. The electric force, we know that the electric force is the electric field multiplied by the charge. So electric field multiplied by E. However, we also know that the electric field is equal to the voltage divided by the distance between the ends, divided by L. Okay, so we have, what do we have? We have the electric field, which is the voltage divided by the length of the rod multiplied by the charge. And because we know that they are balanced, the forces must be balanced. So we know that the electric force equal to the magnetic force. That means that V divided by L multiplied by E is equal to BEV. So E cancels the voltage. So the voltage is BVL. Of course, this is only if the velocity is perpendicular to the um, to the field, and also if the rod is perpendicular to the field. Okay, so it's slightly more complicated if we. How do we know that the forces are balanced? Well, because if they are not balanced, for example, if the magnetic force is bigger, then charge will be gaining at the bottom. And if the charge would be gaining at the bottom, the electric force would increase. The electrostatic force would increase. And it would be increasing until they are equal. Now, if the electric force was bigger, then the electrons would be pushed away from the bottom and the rod would discharge until the forces are balanced again. So the voltage at the end, so this is called the motional EMF. Motional EMF. At the ends of the rod. Now, if there's an angle, you would have a different expression. So you would have BVL sine theta. So actually BVL sine theta. If the rod is not perpendicular to, or the velocity is not perpendicular to the field, but never mind. It's BVL for simplicity for now. Does that make sense? Did I answer your question, Edith? That how do we know that the forces are balanced? Well, theta is defined depending on what is if you have an angle between the velocity and the rod, for example. If the rod is, I don't know, like this, and you're moving like this This is the velocity, and this is the length of the rod. Then, of course, the vertical distance between them. So that would be the angle. This one, theta. If there's an angle between the field like this, the field is going like this, and the rod is moving like this, then it would be the angle between the velocity and the theta. It very much depends. You see, I don't want to go too deep into this because we'll get lost in the angles. Right? You always need to come back to a single electron and see what happens. It happens with that electron. Okay. And it's in example 1, like very beginning of the paper. Just look very carefully at it, and it should make sense. And there are videos on that. Now, let's say we have not a single wire. This is a single wire. So this is a single metal rod. A single wire. Just sorry, apologies. Just need to see something. Okay, and this is a single wire moving through a magnetic field. Let's say we have a frame. We have a frame of wire, so basically a loop of wire. For simplicity, well, a rectangular loop. So B, rectangular loop. Triangular loop. Now, if you have a rectangular loop moving through a uniform magnetic field, now there is in A, B, C, D. In A, B, the voltage in AB is equal to, so the EMF, sorry, it's the EMF. EMF in AB is equal to, well, let's call it A, L, let's call it W, sorry, W, the width, L. And the whole thing is moving with velocity V. This is L, this is W, is equal to W, B, V multiplied by sine of the angle. But sine of the angle is 0. There's 0 angle between the velocity and the wire. Therefore, it is 0. The EMF in DC in a similar way is 0. The EMF in AD is in AD. Well, we have the electrons move down, so we have an EMF. Basically, it's as if we have an EMF in the we have a battery here which pushes the electrons down and the positive charge up. So EMF, and it's equal to L BV, and the EMF in BC is also EMF in BC is equal to LBV. But one is pushing the electrons clockwise and the other one is pushing the electrons anti-clockwise. So the total EMF is 0 volts. So if you have a rectangular loop in uniform field, there will be 0 total EMF in the loop. There will be no EMF. There's no current in the coil. No current in the coil. Current in the coil. Does everyone understand what I have done just now? Please let me know. Do you understand? Now the next part, C, is a rectangular loop. Rectangular loop moving into a field. Right. So basically what happening is the frame moving into a field. So we have a field. Now there's a frame, and the frame is halfway into the field. So basically AD is outside the field, AD, but BC is in the field. So in this case, EMF produced by AB is equal to EMF produced by DC is equal to EMF produced by AD is 0. But the EMF BC is equal to, well, same, BVL. And because that's the only source of EMF, so you have plus minus, that's the only source of EMF, there will be a current in the coil. So BC acts as a battery. The section BC acts like a battery. And there is a current. There is current in the coil, which is cool. And it's a low resistance loop, so the current can be massive. The current can be very large. So when we have a loop moving into a magnetic field, there's a current induced in the coil. And you've seen this. I mean, I bet you've seen this. So Faraday's law. Not this one, no. So you have a magnet, and if you take a field meter, you can see that the field here is very strong, but the field here is not very strong. 0.29 compared to 24. Okay, so weak field. So when we move from here to here, we move into the field and out of the field. So this is a coil of wires. So this is a rectangular loop. And you can move it into the field of the magnet. Look what happens. If when I move it into the field of the magnet, the light flashes. It doesn't flash very. That's better. So when I move it in, the light flashes. I can also move it like this. I can move the magnet. But they've taught you a slightly different thing. They probably you've been taught in school that when the magnetic field in the coil changes, there's a current induced in the coil. There's an EMF induced in the coil. But this is like the foundation of this, because you can see that one end, because we have an imbalance, one end is inside the field and one is outside the field, we have EMF. And finally, we have a rectangular loop moving in a non-uniform field. That's an also 3. So D, non-uniform field. So we have a coil, and you can see that, for example, the field looks like this. So how do we know the field is non-uniform? Yeah, field getting weaker. I'm pretty sure the vertical lines should get weaker as well. So it kind of should look like this. But let's not get into details. They should spread out vertically as well, but it's just awkward. Just going to be awkward if I do this. Yeah, okay, let's keep it. I hope you get the point. Field getting weaker, and you have a frame moving in this coil. So now we have the two ends, the two edges, A, B, C, D. We can see that BC is in a weaker field. And that means that EMF AB is still 0 and EMF DC is still 0. But EMF in AD is equal to BAD multiplied by VL, and EMF in BC is equal to the EMF in BC multiplied by VL. And the total EMF is going to be this minus is because they are in the opposite direction. I could say minus BC. It's going to be BAD VL minus BC VL, which is VL multiplied by the difference of the magnetic fields at the two regions BC, or simply delta B. So a current is induced. BC is in a weaker field. So EMF AD is greater than EMF BC. Therefore, current flows in the coil. So Faraday's law, Faraday, the great Faraday, said that an EMF is induced in a coil. So Faraday's law, Faraday's law is that an EMF is induced in the coil if the magnetic flux changes in the coil changes. So the simplest way, the magnetic field in the magnetic field in the coil changes. And in these two cases, the magnetic field in the coil is changing. So it's increasing in this case. The magnetic field in the coil increases. And here the magnetic field in the coil decreases. And yeah. So flux phi is flux, and it's equal to BA cosine theta. BA cosine theta. So what does that mean? Well, that you have a plane. It has an area. You have a magnetic field passing through. Magnetic field. And area. And if you have the normal line, this is the normal vector. The normal vector to the plane. Theta is the angle between the normal vector and B. Theta is angle between N and B. Okay. N and B. Right. So we have the flux. We have the flux. And Faraday's law says that the EMF is equal to the negative change of flux through time. And go also to the bottom. Yes, and can also go to the bottom. I mean, n can go that way. Yes. That just gives you a positive or a negative flux. It's like a matter of choice. It's when you're doing kinematics, you say, oh, up is positive, right? So a flux going that way is positive, a flux going the other way is negative. So it doesn't really make a huge difference. So Faraday's law says that if you have a changing flux, you have an EMF. You have a induced EMF if you have a changing flux. So if the flux is equal to BA cos theta, there are three different ways how to change the flux. You can change the area. To change flux, you change flux. You can change the area, you can change the field, or you can change the angle. There are three different ways of changing of creating an EMF. Faraday's law. All right. So if you have a if you have a frame, if you have a metal frame, it's a metal frame. So A, changing area. And you have a metal rod. The metal rod is allowed to slide from left to right. Okay, so this rod is allowed to move like this. So metal rod. If there's a magnetic field present, moving the rod changes the area of the loop. Okay. So the area, let's call this side, we call this side X, and this is L, the width X, and it's moving at a rate V, and the magnetic field is uniform, and it is B. All right, so the motional EMF, sorry, the EMF is equal to minus d phi over dt minus d ba cos theta divided by dt. Now theta is equal to 1, sorry, theta is 0 degrees, of course, because the loop is perpendicular to so theta is equal to 0 degrees because the loop is perpendicular to the field. All right, so imagine you have a rod moving through a magnetic field, there's a loop, and because the area of the loop is increasing, you have an EMF produced in the loop. And B is constant, theta is not 0, so it's going to be B, and and area, of course, area is equal to L times X. Area it's a rectangle, L multiplied by X. So it's B minus B, D Lx divided by dt, which is minus B. L is constant, so it's minus BL dx dt. Can somebody remind me what is dx dt? V. BLV. Does that look familiar to you? Does that expression look familiar to you? Theta is not 0 degrees, so cos theta is 1. Cos theta is 1. EMF is equal to BLV. Where did we see that? Have we seen this before? Motional EMF, of course. So it's a rod moving through a magnetic field, produces an EMF, which is VL. And that's the same. We have got the same result by increasing a loop. So a really cool thing about Faraday's law is that Faraday said doesn't matter how you change the flux. If you change the flux, there will be an EMF induced. Okay, do you understand this example? The example A of changing the area. On a scale of 0 to 10, please. Or based on the fact that 3 people have left, I'm I'm thinking right. All right. Okay, Biranavan, do you understand that changing the area changes the flux? And changing the flux produces an EMF. All right. The rest is maths, okay? I'm just showing you how you can, because this is Faraday's law, and what I've done here is I said, well, flux is BA cos theta, but cos theta is 1, so it's BA. And area is LX, so BLX, because area is the area of the rectangle, is L times X. That's this area. So what I'm doing is I'm saying that I'm differentiating this. I'm just finding the derivative dt. And because B and L are constants, so it's going to be BL multiplied by dx dt. With a minus, of course, because it's Lenz's law. I'll talk about the significance of the minus in a bit. And dx dt is v, so it's minus BLV. Is this better? Okay. So EMF is minus d phi dt, which is that, and which is the same expression as the motional EMF, which is really cool. I don't know. I think it's cool. Now moving on to changing the field. Well, let's say you have a loop of wire. You have a loop of wire, and the magnetic field changes with time. B of t. And the area is, well, let's call it L and W. And yeah, so we have B changing field. Let's say the field is as a function of time changes as 0.3 plus 0.01 t Tesla. Okay, so initially the field is 0.3 and it increases as a function of time, right? So as B increases with time, and you can do the same thing. So you have the flux, which is equal to BA cos theta. Cos theta is once again 1. So it's going to be B. Let's say W is 0.3 meters. This is L is 0.1 meters, and theta is 0 degrees. Theta is 0 degrees, so it's going to be B multiplied by A, which is L times W, multiplied by cosine theta, which is 1, which is 0.3, 0.03B. But we know B. We know that B is 0.03 multiplied by B, which is 0.3 plus 0.01 t. which is 0.009 plus 0.0003 t, and then EMF is minus d phi dt. So you just differentiate that, which is minus 0.0003 volts. Very straightforward. Like, the beauty of the Faraday's law is that you just write down an expression for phi and you differentiate it to find the EMF. And C, changing the angle. So let's say we have a spinning C, changing angle. So we have a loop of wire. That can spin. This is the axis of spinning. So it can spin, let's say, clockwise. And there's a magnetic field. There's a uniform magnetic field, B. And the angle, theta, angle changes with time. So theta is omega t, right? So rotational motion is omega is the, yeah. So we have a coil of wire. So we have a magnetic field and a coil of wire which spins like this. So if this was a coil, a rectangular coil, so it spins like this. So the angle is omega, which is the angular velocity, multiplied by time, which makes sense. And therefore, you have phi, which is equal to B A cos omega t. And EMF is minus d phi dt, which is minus BA, which are constant, multiplied by d of dt of cos omega t. So EMF is minus BA omega multiplied by sine omega t, but with a minus of plus. Ooh, interesting. EMF now depends on two things. On three things, on the on B, on A, and on the speed of rotation. Would you look at that? The EMF increases if the angular frequency increases. Okay, so you have, if you have this, if you have phi, if you have theta, well, phi, changing as cosine. So this is phi. And then if you draw the EMF, it's going to be sine. So EMF is going to be like this. All right. So the maximum value for phi, that's going to be BA. And the maximum value for this one is going to be BA omega. Okay, you don't worry too much about this. Don't worry if you don't fully understand, but I hope you can see the logic that EMF changes and is going to be a sinusoidal wave. And that's how we generate electricity. We get something. Let's have a look. That's how we generate electricity. Look, we take a magnet. Okay, well, this is not the ideal example because we take a magnet and we spin a coil. We take a coil and we spin it near a magnet, and that's how we generate electricity. And the output of that coil is going to be that. It's going to be a sinusoidal wave, a sine wave. But by just spinning a coil, so the blue is the voltage and the current in the coil as well. So by spinning spinning a coil near a magnet, we get AC current in the coil. And the current in the coil, goes like this. Pretty cool, I would say. Okay, so Lenz's law. I love Lenz's law, but unfortunately I have to go. You will have a whole webinar on the 4th of January. Toby Peterkin is going to talk about these things, Faraday's law and Lenz's law. Do watch the videos that are offered in the assignment. They are pretty cool, especially I've just rewatched the one of the videos. It was the which one was it? Oh, the lecture by Walter Levin. Well, I mean, I would watch that instead of Love Actually this Christmas. I mean, it's really cool. And what else? The Penn physics demonstration of Lenz's law on page 7. Also, yeah. So it's great. Now, I also did last year. I did, of course, I did a webinar on this topic, and you can watch that as well. All right, so that's your Christmas. That's your to watch for Christmas, and have a lovely one to the account. And I'll see you on the 4th of January. I will be just popping in. There's no webinar next week, and have amazing holidays, everyone. See you. You've been working really hard. Well done. Yeah, good to hear. Welcome. See you.